Optimizing system performance involves both host code optimization and kernel optimization. In this module, we are focusing on optimization of the host program. The host code uses the OpenCL API to schedule the individual compute unit executions and data transfers to and from the FPGA board. As a result, you need to think about the concurrent execution of tasks through the OpenCL command queues. There are three major areas to optimize the host code: reducing the overhead of kernel and queuing, optimizing data movement, and scheduling of the compute units. OpenCL supports both data parallelism and task parallelism. Data parallelism is where the same operations are performed on different parts of the dataset, typically a regular structured array. For example, if I have 4 processing units, I could do 4 adds in parallel, as indicated in the diagram on the left, and iterate over a larger dataset. When finished, I could then move on to switch the operation to multiplication and again iterate over the dataset, then switch to subtraction. In the task parallel case, I can group the add, multiply, and subtract operations together into a task and run those tasks in parallel on the available processing cores. When one task finishes, the next task can be scheduled. Both models can be supported on an FPGA, but there will be differences in how the hardware kernels are implemented and scheduled. We can also mix these styles at different levels in our design. Generally, a smaller number of larger compute units or hardware kernels should be preferred over a larger number of small units, as there tends to be an overhead associated with calling each kernel. Reducing the number of kernels and increasing the work done reduces the impact of these overheads. In OpenCL applications, kernels can be enqueued multiple times and then scheduled to be executed on the device. The command to start the kernel can be sent in one of two ways. For the data parallel case, we can use the OpenCL enqueue_nd_range API, and for the task parallel case, we can call the OpenCL enqueue_task API. The dispatching process is executed on the host processor, and the kernel commands and arguments are sent to the accelerator over the PCIe bus. When the kernel is compiled to a single hardware instance or compute unit on the FPGA, the simplest method of executing the kernel is using the CL enqueue_task. The Xilinx runtime, XRT, will schedule the workload on the FPGA. There is an overhead in dispatching commands and arguments to the accelerator. This is represented in the following example. A compute unit has a global work size of 4096 and a local size of 512. This means that there are 4096 items to be processed, each requiring a processing element, and 512 processing elements available in our target. In this case, there are 8 work groups, or the kernel needs to be called 8 times to process all the data. In the diagram on the right, you can see gaps in execution between kernel invocations. These gaps are overheads associated with calling a kernel and are idle time for the kernel. These are overheads that would reduce the system performance, and ideally we want to reduce or eliminate these overheads. One way to do this would be by increasing the local size or reducing the number of work groups and therefore the number of times the kernel executes. For the data parallel case, Xilinx recommends that you carefully choose the global and local work size for your host code and kernel so that the global work size is the same or a small multiple of the local work size. Ideally, it will be the same as the local work size. In the second example, the optimized version, the global and local sizes are both 1. There will be some overhead to call this kernel, but as it is only called once, there will be a reduction compared to the previous example. In the FPGA, we don't necessarily have to increase the number of processing elements to achieve this. We can implement the data parallel style of processing inside the kernel, eliminating the kernel call overheads by doing this at the OpenCL level. To reiterate, CL enqueue_nd_range kernel is supported, but Xilinx recommends using the CL enqueue_task. In the OpenCL API, all data is transferred from the host memory to the global memory first. Remember, global memory is on the FPGA accelerator board. It's then transferred from global memory to the kernel for computation. The computation results are written back from the kernel to the global memory and from there to the host memory. A key factor in determining strategies for optimization is understanding how data can be efficiently moved around. During data movement optimization, it's important to understand and isolate, if necessary, data transfer code from computation code. Inefficiency in computation might cause stalls in data movement. The goal is to maximize the system-level data throughput by maximizing PCIe bandwidth and usage and memory bandwidth and usage. It usually takes some iterations of running mainly hardware emulation as well as execution on the FPGA to achieve this. You can see the methodology flow for optimizing the data movement. We'll start from functionally correct code. Note that as you modify the code, you may need to go back and verify functional correctness, and this step isn't shown here. Hardware emulation will be run to generate profiling data on the host code and kernels, although we are mainly focusing on information that will help optimize host code. We can then analyze the kernel compilation reports, the profile summary, timeline trace, and device hardware transactions to understand the data transfer throughput. Here we want to check PCI utilization, memory utilizations, including external and on-chip memories, and the actual kernel throughputs. The code can be modified to address any issues detected to optimize data movement. The last step is to build and run on real hardware. Again, we can analyze performance. This time we can detect any real-world issues and see the actual data transfer performance. Applications will commonly have larger data sets than can be stored in the available memory on the acceleration device. They require the data set to be transferred and processed in blocks. Techniques that overlap the data transfers with the computation are important for increasing performance for these applications. As an example, we have a kernel where the host needs to write some inputs, execute the kernel, and read back the results. If these commands are carried out sequentially, there will be a large gap between kernel executions while the results are read out and new inputs are written in. Using an out-of-order command queue, data transfers and kernel execution can overlap as shown on the right. The host code enqueues all the tasks in a loop to process the complete data set. Using the OpenCL event object, you can also set up event synchronization between different tasks to ensure that data dependencies are met for each task. Allocation and deallocation of memory buffers can lead to memory segmentation. This might result in suboptimal performance of compute units, even if they could theoretically execute in parallel. This issue often occurs when multiple POSIX or P threads for different compute units are used, and the threads allocate and release many device buffers with different sizes every time they enqueue the kernels. In this case, the timeline trace will exhibit gaps between kernel executions, and it may seem like the processes are sleeping. Each buffer allocated by runtime should be contiguous in hardware where possible. For a large memory, it might take some time to wait for that space to be freed when many buffers are allocated and deallocated. This can be resolved by allocating a device buffer and reusing it between different enqueues of a kernel. Similar to the workgroup and kernel sizes, larger contiguous memory buffers are likely to help increase performance compared to a larger number of smaller buffers, which may cause fragmentation. Where possible, data should be transferred in bursts, and larger contiguous memory buffers will help support this and move data more efficiently. We've already seen that scheduling kernels can introduce overheads and some techniques to reduce these. Ideally, we would only use one compute unit, but this isn't always possible or practical. Scheduling kernel operations efficiently is key to overall system performance. This becomes even more important when implementing multiple compute units or kernels. There are two ways of managing the execution of a kernel. We can use multiple in-order command queues or single out-of-order queues. This shows an example with two in-order command queues, Q0 and Q1. The scheduler dispatches commands from each queue in order, but commands from Q0 and Q1 can be pulled out by the scheduler in any order. In this example, Q0 commands are labeled as 1, 2, and 3, and Q1 commands are labeled as 10, 11, and 12. The XRT scheduler, the Xilinx runtime, can pull the commands from Q0 and Q1 in any order. In this diagram, you can see the command 1 from Q0 is first, followed by 10 and 11 from Q1, then back to the first queue for commands 2 and 3, and then finally command 12 from the second queue. This may or may not be best for the design. While commands 10 and 11 are being scheduled, compute unit 0 may be idle for longer than necessary, and similarly when 2 and 3 are being scheduled, the other compute unit 1, may be idle for longer. It's up to you to manage synchronization between the two queues if this is required in your design. In this case, we only have one queue, but it is an out-of-order queue. The scheduler can dispatch commands from the queue in any order. In this example, the commands are scheduled in the order 1, 4, 2, 5, 3, and 6. Again, if it's required, you must manually define event dependencies and synchronizations to schedule commands in the order that you need for your design.